Potential-induced degradation, appearance shunting and polarization type of degradation are not optically visible, however advanced stages of corrosion or delamination type degradation are visible. Potential-induced degradation causes a progressive power loss, and some degradation modes may also manifest in discoloration and hot spots over time. Potential-induced degradations can be detected through infrared thermography imaging of operational solar modules in direct sunlight or in the laboratory, where degradation appears as warmer cells close to the bottom frame or patchwork patterns, and is more significant in solar modules positioned close to one of the poles of the solar string. Shunting degradation is also detectable by electroluminescence imaging, especially under low current bias, like 1/10 rated current, where the affected cells closer to the module frame show reduced luminescence. Shunting degradation causes a decreased shunt resistance, FF, and voltage in the 4 curve, and is more noticeable under low light. Polarization degradation shows a decrease of luminescence and no low current bias dependency, being harder to detect with electroluminescence images. 4 measurements can be used to confirm the presence of potential-induced degradation in combination with infrared thermography or electroluminescence. Polarization degradation causes a decrease in short-circuit current and open-circuit voltage, typically originating on the rear side of p-type base cell modules, like PERC, and the front of those using n-type cells, for example PERT, TOPCon, IBC. Potential-induced degradation is a degradation mode induced by a high voltage stress with respect to ground. The occurrence of this failure depends on the magnitude of the voltage, number of serially connected solar modules per string, and the polarity of the electrical field buildup between the framing and glass surface and the solar cells. The last depends on the inverter typology, transformer, the grounding concept, and cell technology. Modules with p-type cells degrade in negative polarity strings, whereas modules with n-type cells in strings with positive polarity. The degradation is accelerated by elevated temperature, humidity, rain, surface wetting, condensation, and soiling. Polarization degradation is caused by the buildup of surface charges on the cells, which results in a current loss. Shunting degradation is induced by leakage currents coming from the displacement of sodium-ion ions from the module's front or rear glass and through the encapsulation material. The flow of sodium-ion ions creates shunts in the cells. For both degradation types, module and cell design has a fundamental influence if and how much a module is affected by degradation. There are modules on the market that are designed to be degradation resistant. Yield losses of 20% and more within 1 year were observed in the past. Due to its catastrophic performance loss, degradation bears a high economic risk. Shunting degradation is to some extent a reversible polarization type and can therefore be partially reversed or stopped when detected in time. However, if detected too late, it can lead to irreversible power loss. The polarization degradation effect causes instead a significant reduction of short-circuit current, open-circuit voltage, and power. Polarization degradation is thought to be fully regenerated by reversing the polarity of the bias potential. In some cases, material degradation of the modules through corrosion and delamination occurs associated with excessive leakage current. Up to now, safety problems directly related to the degradation have not been reported, but hot spots and corrosion caused by the strong cell mismatch may cause such safety issues.